Sounds good. So I'm going to be talking about combining social choice and matching to understand institutional stability. Let me start on a slightly philosophical note by Douglas North. He says institutions are created by human beings, they evolve and are altered by human beings. So oftentimes in economics, we study organizations and we think of the institutional rule that we exploit as some exogenous thing. But here, this quote kind of explains that the design of many institutions is very much a deliberate collective choice, and that these choices can change over time, right? So this gives rise to the question of stability of institutional choice. And within an organization, different coalitions are often mobilizing and trying to change the institution and relax the constraints that work against them. So this paper is going to study, endogenous choice and stability of an institution that's going to shape all types of, performance and evolution of organizations. So in particular, in many organizations, the matching mechanism used to assign members to positions is itself an institutional choice, right? So here's some examples. For example, in the US Senate, political parties assign their politicians to legislative committees. They have to figure out how to design these systems. In India and in other places, the bureaucracy has to structure internal labor markets. Even in private firms, such as Google, this third bullet point, personnel are organized internally using different types of mechanisms. And in these particular types of applications, the choice of the institution is chosen, agreed upon, and influenced by the very people who are being assigned. Okay, so this is kind of a different type of setup, which is it's not an Al Roth coming in and saying, here's the matching mechanism, is these people collectively agreeing upon how to design the system to allocate themselves. Okay, so that's what I'm going to focus on in this talk. So I don't need to tell this audience that who gets what position is going to affect all types of aspects of an organization's performance, synergies and conflicts between the members, aspirations, and so forth. Of course, agents' preferences can also change over time. For example, if you're thinking about this politicians being assigned to committees, different legislative battles might come up, or jurisdictions of who gets what power in which committee changes, and agents' preferences change. And also the organization's members themselves may change over time, right? So what all this implies is that different coalitions are often going to be mobilizing and trying to lobby for changing the institution, in this case, the matching mechanism. And perhaps a successful institutional design is one that can endure some sort of endogenous pressure for reform, right? So I'm going to discuss different versions of what I call institutional stability, which is going to consider the stability of the matching mechanism, the institutional structure itself. Okay, so namely, in what environments do we get a matching allocation such that no decisive coalition can change the mechanism or allocation in favor of an alternative allocation that it prefers? And importantly, this alternative allocation can potentially lead to a loss for people who are not in the coalition. Okay, so this is bringing together two mostly distinct literatures, social choice and matching theory. This is going to be social choice, where the object of choice is a matching allocation, a vector of assignments where different people are getting different seats. And institutional stability is going to kind of protect against alternative allocations that endogenously generate both winners and losers, right? So a standard setup of one-to-one matching and one-sided matching. So only agents are going to be assigned to seats. Only agents have preferences over which seats they want, their own assignment. That's going to lead to preferences over two different matching allocations. And we're interested in different preference aggregation rules, different voting rules that determine how people vote in favor of one matching or the other. Okay, so let me start off with a few assumptions, all of which I'm going to relax at the end of the talk, but just to, for ease of exposition. So I'm going to assume that all possible allocations are going to be feasible. Each agent is going to give a complete, untruncated set of preferences. All preferences are going to be strict. The market's going to be balanced, so the number of agents is the same as the number of seats to be assigned. And a big assumption, which you might not like at the start, but I'm going to relax this in a very major way at the end of the talk, which is that the agent only cares about his own seat that he gets, his own assignment. Okay, so if he gets the same assignment in two different matchings, he's going to be indifferent. If he gets a more preferred seat in one matching relative to the other, he's going to have a strict preference. Okay, so I'm going to assume for now the agent's preferences over two allocations is solely determined by what assignment, what seat he gets. So you can think about a variety of different voting rules, right? We all know Pareto efficiency, it shouldn't be the case that some people can be strictly better off, but no one's made strictly worse off with an alternative allocation. This is basically unanimity rule with the indifferent agents abstaining. You can think about a weak Pareto efficiency, where you shouldn't have an alternative allocation that everybody can be made strictly better off, right? There's a large, growing literature, more on the computer science side of things maybe, called popular matching, which is basically a plurality rule. So you're looking at the sizes of the sets and comparing the sizes of the sets that prefer a matching M to M prime versus M prime to M, right? And it shouldn't be the case that you have an alternative matching such that a larger group prefers M prime to M, okay? And I'm going to add to this, set of different voting rules, majority stability. So a matching M is going to be majority stable if there doesn't exist an M prime, such that the number of people who strictly prefer M prime to M is a majority, okay? N odd, so the size is at least N plus 1 over 2. And in this talk, I'm going to kind of compare across a bunch of these different concepts. So, what follows strictly immediately from these definitions is the following set relations of allocations for a given set of preferences. Okay, so what you'll see is popular matching is fully inside Pareto efficiency and majority stability, but majority stability and Pareto efficiency are not contained in one another. Okay, so just to keep this in the back of your mind. So these notions are, of institutional stability are slightly different from stability, particularly in one-sided matching, where we're dealing with blocking pairs or coalitions that are trading amongst themselves, right? Some notion of a core, that's more of a local deviation. Here, we're allowing larger global coalitional deviations where potentially the coalition improves at the expense of others, okay? And how does this compare to normal social choice? Well, in social choice, all agents are getting the same exact assignment. In this case, the object is a vector of assignments where each of us are getting different seats. And this is going to impose intricate restrictions on what preferences of agents can have over the allocations. So it's going to be a subcase of social choice, but I think one that's kind of substantively important and highlights endogenous envy within organizations and so forth. Okay, so I'm going to structure this talk across 3 questions that you can ask when it comes to institutional stability. So given a set of preferences, when do these different notions of institutional stability exist? Can you characterize such set of preferences? Then you can ask a more basic question. Given a set of preferences and a candidate allocation, can you test whether it's institutionally stable? And lastly, given a notion of institutional stability, which mechanisms are more or less robust to admitting institutional stability? Okay, so I'm going to try to address these questions one by one. So the first question, can we characterize preferences where these institutionally stable allocations exist? So Pareto efficiency, as you all know, is super easy. Commonly used simple mechanism like serial dictatorship will guarantee it. Of course, if you have weak preferences, the tie-breaking can matter. But if you have strict preferences, something like serial dictatorship is going to work. This is unanimity rule, right? The issue is oftentimes with such a rule, you're going to get kind of senior dictators, right? So in this example, as you see, people 1 and 2 are holding back an entire chain of improvements in the matching of others. The matching is given in bold, right? So proofing against unanimously approved improvements is kind of a low standard when it comes to institutional stability in reality, where oftentimes institutional change creates both winners and losers. Okay, so popular matching creates both winners and losers, and this literature basically started from this paper Abraham et al, and it fully characterizes what a popular matching looks like. So a matching is popular if every seat which is someone's first choice is assigned, and each person is assigned to either their first choice, what's called an F post, or their highest rated choice that's not someone else's first choice, an S post. Okay, and many of the folks in the audience actually have work on this topic. So let me just reiterate that definition because it's important. So each person has to be assigned to either his top choice or his highest rated choice, highest ranked choice, that's not someone else's top choice. Okay. You can also have popular matching of different sizes. So you just add to your preference list a last resort option of not being assigned. Okay, so that could be your S post. So this is plurality rule. Just to make sure this concept is clear, here's an example at the bottom. You see that A, B, and C are folks' F posts. And for example, for person number 1, D is the highest ranked choice that's not anyone else's first choice. Okay, and the way you can have popular matchings of different sizes, which are not complete matchings, is that sometimes an S post can be the outside option of remaining unmatched. Okay, so I'm going to focus in this talk on complete popular matching. Okay, everyone is assigned. We have strict preferences in a balanced market. And what I just want to highlight is that this leads to a very stringent conditions for existence, right? So the next few points are just going to, follow from this characterization using Hall's marriage theorem. So of course, a necessary but not sufficient condition for complete popular matching to exist is that the F post and S post span the set of seats, right? So here's an example. The F and S posts are in bold, and you see that object F is no one's F or S post, right? So you're not going to get a complete popular matching in this scenario. Moreover, oftentimes in practice, you will have certain blocks of preferences. What do I mean by that? Well, as you see here, everyone prefers A and B over C and D over E and F, right? Well, for there to be a complete popular match, you can't have 3 or more blocks, right? Because any of the blocks after the second block is going to be no one's F or S post. Moreover, if you have 2 blocks, you have to have it's necessary to have that each of the objects in each block is someone's top choice within that block. So for example, here, object E is no one's top choice in the second block. So again, you fail to have a complete popular match, right? And so thus far, these were kind of restrictions over preferences, what preferences can look like. Even if you fix in particular type of mechanism, you have further restrictions. For example, if you're trying to implement a complete popular matching with a serial dictatorship, it needs to be the case that the people who are getting their F posts in this popular match have to be more senior than the people getting their S post, right? So here, again, the F and S posts are in bold. If you have the seniority ranking that 1 is more senior than 2 and 3, you get A, B, C. But what's the problem here? Well, in any of the 2 popular matchings here, person number 3 needs to get B. And hence, he has to be more senior than the people getting their S post, right? So you have restrictions on preferences, what preferences can look like. You also have kind of what seem to be some stringent restrictions on the details of the mechanisms. So let me show you this example here, where the matching that's here in bold, A, B, C, D, E, is majority stable but not popular. So you can immediately see here that there are 3 blocks. Everyone prefers A to B to C through E. So you already know that there's no popular matching here. But this matching in bold is majority stable. You cannot get a majority strictly better off here. And what's happening here? Well, there's a basic fundamental packing problem, right? The packing problem is the following, that you cannot reallocate an entire majority to a new set of seats. So sorry, the packing problem here is that to get majority instability, you have to change the assignment of a majority of agents, and you can't move a majority of agents into a minority of new seats, right? So here, for example, as you see, everyone is envious of A and B, but to get a majority here, you need to move 3 people, and you can't put 3 people into 2 seats, right? And this packing problem is going to kind of cause a lot of differences with respect to majority stability, as I'll show. Okay, so majority stability, of course, all these notions of stability are going to be affected by how correlated preferences are, right? The more correlated preferences are, the more envious you are of each other's allocations, and the larger the sizes of coalitions you can move, right, to alternative allocations. and be strictly better off. What I'll show you here, these are two very related examples. I've only switched two different preference seats here between left and right. The correlation is actually higher on the left, but you see that you have this majority stable allocation, the same as the previous example. And these small changes actually decrease the correlation in preference, but no longer do you have any majority stable allocations, okay? So what's the problem here? Well, to address this packing problem, you need to have chains of envy, right? Such that, let's say Rustam is removed, I take Rustam's seat, Alex takes my seat, Peter takes Alex's seat, and so forth, right? This is the same example in kind of looking at the graph of envy, which agent is envious of whose seat. What you see here is the packing problem at play. You can't move a majority into a minority of new seats. But when I change this mechanism slightly, when I change the preferences slightly, you get this chain of envy in red. Okay. So as you saw from this example, these chains of envies are going to be kind of imprecisely captured by correlation alone, right? So again, to reiterate, the packing problem arises because you can't move a majority of people into a minority of new seats. You need to have these chains. But what makes majority stability kind of surprisingly robust to exist is the fact that you need these chains of envy. So, for example, in the US Senate, the Appropriations Committee that controls the budget of all the other committees is a very prestigious, highly sought after, very powerful committee. So it tends to be kind of people's top choice. If you wanted to have a complete popular matching in this case, you would have to have n-1 agents to have all distinct second choices. Not going to happen, basically, practically. But the packing problem is still going to allow for potentially existence of majority stability because you can't put everybody into appropriations. Okay, so this is the kind of interesting robustness that you see with this when you're looking at majority stability. So not only, if you're going to get majority instability, not only do you need enough envy, you need enough people to be envious of each other's positions, you need to have these chains of envy, right, to address this fundamental packing problem. And envy needs to be in all the right places. If you have multiple chains originating from the same agent, this is going to be superfluous, right? So what you see from kind of some simulations here, I'm plotting on the x-axis how correlated agents' preferences are. And on the y-axis, for a bunch of different simulated tries, what fraction of preferences admit majority stable allocations, okay? And even for kind of sizable preference correlations, so like 0.5, let's say, 75% of these instances of preference simulations, you are still getting some allocation that's majority stable, okay? So to give you, this is matching in practice, so give you some idea of practice, in the Indian Civil Service, something I study, preference simulations at the preference correlation at the highest are about 0.5. And this causes a lot of imbalance in assignments, which my paper shows. But even for such kind of correlated preferences where people don't want to go to this, let's say, the distressed areas of the country, you're going to get these systems that are not always changing, right? People are still, a majority of agents will still not potentially be able to move and change the institution. So I don't, of course, have time to go through the simulations, but as you might expect, as you increase correlation, the maximal size coalition that can change and be strictly better off is increasing. Complete popular matching is going to fail to exist even with a small amount of correlation in preferences, but surprising kind of robustness you find with majority stability. Okay, so then let's think about in which cases can you characterize nice environments for majority stability, right? So you might think that what we know from social choice, there are these nice restrictions on preferences, right? Weakly single peak preferences, order restrictions, and so forth. What I can show is that these basically have no bite in this social allocation choice problem we're studying, right? Social choice over matchings. So let me just show you, let's see how much time. So what I find is there's no possible set of weakly single peaked preferences for a market size greater than 3. Here I've showed you the only way that you can have weakly single peak preferences for a market size of 3. Okay, so agents in black are 1, agent 2, agent 3. I've kind of shown you the preferences in the usual sense on the right. And here a column is the matching, right? So here's the order over matching such that you get weakly single peak preferences. And you should notice this kind of symmetry and anti-symmetry here, right? So person 1 is fully symmetric and person 2 and 3 are opposite anti-symmetric in some sense. And the proof is very easy. Suppose you had a 4th person who's going to be indifferent over all those allocations where he gets, let's say, D. You know that this is the only way to have single peak preferences for these other people. He's going to have some preference, person number 4, let's say he prefers D to C. That means that these allocations where he gets C are going to be to the right or left or on either side. And that means immediately a violation of weakly single peak preferences for, let's say, person number 1. Okay, so a standard trick of single peak preferences is not going to work here. It's not going to give you a nice set of preferences to work with. Similarly, I can show that order restricted preferences. This is when you when you set an order of agents such that the people comparing any 2 matchings, those who prefer one to the other are to one side of those who are indifferent or to the other side of those who prefer the opposite. This is not going to, you're not going to get a possible set of order restricted preferences for market size 3 or higher. Okay, and the intuition you should have here is basically there's an intrinsic rivalry when you think about matching. Namely, when I get object A, Rustam is left with B and Alex is left with C, and so forth. And this is exactly what you saw with this kind of quick proof sketch of why single peak preferences doesn't work, right? So the other complication is that as soon as you change the status quo, the entire graph of envy, who is envious of whom, changes, right? So the standard tricks are going to fail. You can think about some constructive approaches. So it's useful to know that, of course, if preferences admit a majority stable allocation, there's going to exist a allocation that's both majority stable and Pareto efficient. Just run top turning cycles, right, and improve. And using this fact, sort of what you might expect as 2 envy minimizing algorithms, right? Minimizing the average preference rank, or greedily minimizing the preference rank. So this is you can think of the best possible tie breaking for a Boston mechanism, basically. These algorithms are going to be kind of pick up a majority stable allocation if it exists very often. Okay, they're not going to be 100% proof though. So here's an example. I don't have time to go through the example. The underlined objects and the objects in red are these 2, minimizing average preference ranks, greedily minimizing preference ranks allocations. And it turns out they both fail to pick up the only majority stable allocation that this set of preferences does admit. And this crazy thing to do here is to give number 6 his worst possible choice. But that allows everyone else's allocations to be such that there is no coalition to move. And this is basically, I am hoping to convince you that this makes this concept very hard to characterize because of these kind of very wacky cases. Although greedily minimizing preference ranks or minimizing the average preference ranks does go a long way. Okay. Fortunately, though, checking whether something is majority stable is super easy, right? So for a given set of preferences and a candidate allocation, I can immediately check whether something is majority stable. The basic idea is you have an integer linear program. You're thinking about what reassignment matrix you can form given an envy matrix, and trying to maximize the envy that's realized. And the fact that the alternative allocation is also a matching is going to allow the linear program to have integer solutions. So this is very computationally simple to check. Okay, so that's a good thing. We can check. Characterization is harder. Some quick,
I'm sorry, you have 1 minute.
Sure. So it turns out that for serial dictatorship, when you're comparing serial dictatorship in a given order of seniority and Boston mechanism with the same tie breaks, assuming truthful telling, it turns out that Boston mechanism actually does a lot better. You can get smaller coalitions and this is basically because this favoring higher ranks property does wonders. Okay. So practically speaking, there's very few cases where a serial dictatorship will give you something that's stable, but a Boston will not. So I mentioned I'll end with this last note, which is that thus far I've assumed that a person I only cares about his own assignment, right? Let me relax that to say that I never will vote against his own assignment, but he could have any possible set of preferences over two matchings where he has the same seat. Okay, so I could say that I really like Peter, I want to make Peter better off. I could say that if I get allocation A, then Peter should get C, and so forth. All types of enemies, allocations, coalitional preferences, what I will call selfish but interdependent preferences. You will find that this only leads to more instability with majority stability. Okay, this is not true for popular matching. You can come up with this unidirectional effect does not hold. And what's important here, as I said, is correlated preferences at play. Well, you can also come up with similar results to McKelvey. So if you have perfectly correlated preferences or even close to fully correlated preferences, you can have a majority approved path from any assignment to any other assignment. Okay, so let me just end here saying, despite certain systematic correlations in preferences, politicians really want certain committees, Indian civil servants really want to avoid certain areas. In majoritarian institutions, they might not lead to change in the mechanism. And you might expect change in the mechanism when you have certain shocks that increase the correlation preferences. Let's say a political party sweeps a geographic region, or a crisis leads to a lot of alignment in which committee has power and which committee is sought after. So thanks very much.
Thank you very much.